Now, this, again, very much kind of towards the end of the differentiation and integration of year 13 content. We're looking at how we can combine derivatives to have a particular net effect. So ultimately here, like this is the same as, like that would cancel with that. So this combination of derivatives ultimately would mean the same thing. Okay, so it's possible to like express the chain rule in that form if we think of like y as equal to f of u and u equals to g of x. This is literally what we were just doing. But if this confuses you, just use the process as we said. So basically think of dy dx, the rate of change with respect to x, and then it's a combination of the two things. Oh, so I'll leave that there if you wanted to check that. So for example, you can do this for other variables as well. So for example, if we had dv dt, rate of change of velocity with respect to time. Okay, so we're going to see how we can manipulate rates of change of different things as we go forward. But what we'll do is we'll look at this kind of idea now. And it's quite common that we'll use something dt because it will be with respect to time. And in a real life model, it's normally time we're modeling against. So consider the rate of change of volume, v, of a sphere with respect to time if the rate of change of its radius is a constant k. Now, sometimes in the exams, it will be like someone blowing up a balloon and you're looking at how the radius changes, right? How does the whole volume change? How does the surface area change? So there's lots of things to tie together. Now, what we can say is that dv dt, if we look at what derivatives we might have, well, if I know something about the rate of change of radius, could I just point out if they just say rate of change of something like radius, they mean dr dt because it's with respect to time. How is the radius changing? So we know dr, put that there for a minute. They've told us something about dr dt. Now to compensate, I ultimately want dv dt. So the derivative I've kind of got to invent or find is dv dr to have that net effect. Now what they've also told me is that this thing, hang on, change color. Is a constant. Okay. And this is the kind of question where you almost have to invent a formula or know a formula to do with mensuration, to do with volumes, area, surface area, something to do with volume and radius for a sphere. And these are worth knowing because I'm not sure all your exam formula books will give you these. So volume is actually equal to 4/3 pi r cubed, which you would have done at GCSE for a sphere. But that now gives you a formula that you can differentiate. And if you differentiate, just like if it was y and x, the derivative you'd actually be working out would be dv with respect, like dv dr. Okay, and let's do that. Differentiate the volume with respect to the radius. So let's do that. dv dr would equal, now the power we're dealing with is of r, so we're going to times it by 3, so it'd be 4/3 pi times 3r squared, and the 3's would cancel, and this would actually give us 4 pi r squared. Interestingly, notice that the volume of a sphere differentiates to give it surface area, and there are reasons for that. But therefore, what that means we can do, take this back up here, therefore, Sorry, I'm going in a weird way because don't want to hit this weird bit of the screen. Takes me out of the PowerPoint. So I end up with 4 pi. I'm going to put k r squared. So basically this times this. That's what we've done. So I've times that by the constant. Okay, so we've found this derivative, that thing, and we've just times them together. Okay,